if 6 dice are thrown, what is the probability that exactly 2 of them are 6? In other words, you have 6 of them. You have these 2, but then there are 4 other rows, and these other ones are some other numbers. Something like that, okay? Yeah. That'll be like one example of getting this, okay? So what's the probability of getting something like that, okay? All right. One nice thing about math is, from math you can learn a lot of skills, but one of the problem-solving skills that you should learn is to simplify the problem just for that question. Okay, so of course when you throw a die, you may have like 1 or 2 or 3 or 4 or 5 or 6, but for this question we really don't care about what other numbers there are. It's either 6 or not 6. Okay, so we can, instead of talking about the numbers, we can just say this is like yes, yes, no, no, no. And that'll be like one way, right? Okay. And then, of course, you might have like the 6 turning up on the second and fourth die, and then something like this could be a possibility, right? Where y corresponds to number 6 and n corresponds to whatever else, right? Okay. And that one, we're used to it, right? How many ways can you have different ways to get exactly 2 6s?
15.
Yeah, how do you calculate it?
6 factorial over 2 factorial.
Yeah, it's 6 choose 2, right? Which is 6 factorial over 2 factorial times 4 factorial. This divided by this will be 6 times 5, and then you divide by 2, that will be 15. Very good. So you have 15 different ways to achieve this, which means now you just have to figure out what the probability of individual ones are, right? And then once you figure that out, you can just multiply by 15 and you're done, right? So that's the idea, right? Okay, so now let's try to see what's the probability of getting exactly this sequence, y, y, n, n, n. So you should think of this as what we just did, like having 6 on the first row, 6 on the second row, and then some other number in the 3, 4, 5, 6 rows. Okay? So what principle is at work? It's the product principle that we're using, right? So this will be like probability of rolling a 6, right? Probability of rolling another 6. Right? Under the condition that the first row was a 6, but does that really change the probability of the second one? It doesn't, right? So there's a very important idea here that often happens to be the case. I should have mentioned there before, but if you see that an event A happening doesn't change the probability of B, in other words, this is same as probability of B, if this is true, right, then we say A and B are independent. They don't influence each other. Knowing that one happened doesn't change the probability of the other. Okay? Yeah. So in the previous example that we just did, getting the first ball as the red did change what comes next, right? You got lower chance of getting a red if the first one was red, right? But sometimes it doesn't matter, like this example. So, yeah, this concept of independence is very important. So here, this will be independent of the first row. So it's just this, and then probability of no, probability of no, probability of no. So in other words, if this is true, then P A B, A and B, is really same as PA times PB. You no longer have to put the conditional there because they're the same thing. So the product principle just happens to be exactly just the product. So that's what you have. Okay, now let's try to figure out what this probability is. If you roll a die, what's the probability of getting a 6?
1/6.
1/6, right? So you have 1/6 twice, so let's put it as squared. What's the probability of getting a non-6?
5/6.
5 out of 6. So 5 out of 6 is repeated
4 times.
4 times. Okay. So therefore, the answer is 15 times this. But to get a pattern, rather than writing it like this, let's write it like this. So what we're going to do is we're going to say 6 choose 2, 1/6 squared, 5/6 the fourth. Okay? So that will be the answer, whatever that is. That, if you just put this into the calculator, then the calculator will tell you the answer for this one. Any questions? Was that, yes?
How come you have to multiply it by 6 choose 2?
Because the probability of, yeah, that's a very good question. Good point, good point. The probability of this one was 1/6 to the squared and 5/6 to the fourth, right? Now let's think about this one. This will be 5/6 times 1/6 times 5/6 times 1/6 times 5/6. So again, it's just a multiplication of the same thing. It's just different order. So it's still the same story, right? But what's the probability of this? This is like this or that or that or that or that or, right? So when you have or, what do? Do you add or multiply? Or do you? You add, right? So if you have A or B, what's the addition principle? You have to add the probabilities. Of course, you have to subtract if there's any overlap. But here it's a case where you can't have two things at once. You can't have a sequence that came out like that. That's not the same thing as this one, right? They're totally distinct things, so there's no overlap. If there's no overlap, then it's just simply the sum of those two. So what you end up with is like you have this plus this plus this plus this plus this. How many times did you add? 15 times. So done. That's why you have this. Okay? Is that clear now? All right, thank you. That was a wonderful question. I think that clarified the fine point here. Right? Okay, and we're going to define a random variable. Let's call this random variable x as number of 6s when, how many times did we throw? 6 times? Right, yeah. So when a die is rolled 6 times. And what we just, I erased it, but what we just figured out is the following. The probability that x will be 2, the probability that you'll get exactly 2 6s is 6 choose 2, 1/6 to the squared, 5/6 to the fourth. Okay? Now let's try to change these numbers and see if there's a pattern. What will be the probability that you'll get exactly 3 6s when you roll it 6 times? 6 choose 3 because it's 3 yeses and 3 nos. You're shuffling them. Is that okay? And then you have 1/6 third, 5, 6 to the third. Oh, so you already got it. So here's what we found out. It's the probability of x equals to k, where k could be like 0, 1, 2, 3, 4, 5, or 6. Other numbers are impossible, right? Is obtained by 6 choose k, right? 1/6 to the k, 5/6 to the 6 minus k. Okay. That's called the binomial distribution. And we can make this even more generic. Okay? So in the most generic case, I'm going to make this even more abstract. Am I going too far? Are you staying with me? It's okay? All right. All right. Let's make sure that we understand this before I move into the more general case. Okay. So let me ask a few other questions. What do you think is the most likely outcome if you roll a die 6 times and you count how many times you get this number 6? What's the most likely outcome?
X equals 1.
1, x equals 1. So you can kind of expect that p x equals to 1 is the highest number, right? Okay? So, and I want to demonstrate that, so some words here. If this is a function of k, right? So if I say this is f of k, this f is what's called the probability distribution function. So PDF, probability distribution function. Okay. Now, as opposed to this, there's something called the cumulative distribution function, which comes in handy if you're doing like huge calculations. You're going to see, and that's usually people use capital letters for cumulative distribution function. And the cumulative distribution function is sum of all the values of the PDF until it reaches that number. Okay? Makes sense, right? Yeah. So, in other words, F3 really means f of 0 plus f of 1 plus f of 2 plus f of 3, which is same as asking you what's the probability that you're going to get 3 or less rolls. Because this is having 0 6s, 1 6, 2 6s, 3 6s, right? You're adding them up, so that's like all the way, the probability that you're going to get 3 or less 6s, okay? Okay. So now I have to tell you how to get this from using a TI-84 calculator. By the way, I asked you to get a calculator, right? You should bring them for this class. So the way you get this from a TI-84 is you the binom PDF, binomial probability distribution function, okay? And then you have to specify the number of trials, which is 6, and the probability of this thing happening. This is the probability that it doesn't happen, right? One trial happening and not happening, so 1/6. And this k value goes last. So let me show you how it's done. So you can go to second vars. Second vars pulls up all the available distributions inside your calculator. And if you go up, you can see the binom PDF. Right? Now, if I want binom PDF, we decide to do the case when k is 3, when you roll the dice 6 times, right? So number of trials, because we're rolling the dice 6 times, we put 6 for the trials. Probability is 1 divided by 6. X value, what's x here is the k value. What I'm calling k is this x. A lot of books also use x as well. 3, and then I do paste. And what that gives you is the value of the probability, which is 0.0535. Okay. So that's how you quickly get it. Right? Okay. Now, there's something I want to show you. I could graph this, but rather graphing it, let's try to put the picture on the board. Can somebody give me the value of p of x equals 0? What is it?
33.4%.
0.34?
334.
334, okay. All right, so let's just do 3 digits, okay? P of x equals to 1. What do you get?
0.401.
0.401. Okay, p equals to x equals to 2.
0.201.
201. Okay. P equals to x equals to 3.
0.053.
P equals to x equals to 4.
0.008.
Okay. P equals to x equals to 5.
0.001.
Yeah. So it's like the 6th one we as close to 0, right? Yeah. It's as good as x, 0. So now let's try to draw the graph. Okay. So this f of k, this PDF that I talked about, have the following value. Let's say this is 1. So this is half. This will be something like 3. So at 0, this will be the values. Let's say this is 0.33. At 1, 0.4 will be high. This should be much lower. 0.4 is higher, right? And then at 2, it's 0.2, so it's lower. And at 3, it's 0.2, it's like 1/4 of this, so it's very small. At 4, 0.08, so basically it's indistinguishable here at 5, and then 6 is good as 0. So that's what you get. You get this. So that's the graph of the PDF. PDF will have that graph. Another question is, what would be the value if you add this plus this plus this plus this plus this plus this plus this? What would you get? 1. If you add all the possible probabilities, you should be getting 1. Okay, that's another thing. Still another fact is, what's the most likely outcome?
X equals 1.
X equals 1, which you pointed out before, right? Because the probability is 1/6, the most likely outcome is 1. And in addition to this, we also learned of this expectation value, right? So if x follows the binomial with 6, 1, 6, okay? So I'm giving you a new symbol here. This B is for binomial, 6 is number of trials, okay? And 1/6 is the probability of a success, okay? Yeah. So this graph is the graph for binomial process with 6 trials and probability 1/6. Is that okay? Does that make sense? Okay. And if x follows that, then e of x, if you actually calculate e of x, so expectation value, I explained that it's like, because this is 0, this is defined as you take the value of x and multiply by the probability, like this, k times x equals to k, and you add them up, right? So that's the expectation value, right? So what you do is you multiply 0 to this, 1 to this, 2 to this, 3 to this, 4 to this, 5 to this, and then 6 to some other one that I didn't write. It's practically 0. And if you add them up, the value you're going to get will be 1. Which kind of makes sense, right? Because a lot of times you're going to get 0 or 1. Sometimes you get higher numbers, but they occur less often. So on the average, so for example, if you're betting money on this with each number of 6s will give you $1 or something, then if you play this game 6 times, the amount expected that you will earn will be just $1. Right? So you can think of this as this times this. In other words, what I'm trying to say is that this is a theorem, which I don't have time to prove. It's not that hard. It just uses some calculus, so it's also interesting. But I won't have time to prove this. Okay? Is that if x is a random variable that follows np, then expectation value of x is np. The average outcome that you will see will be n times p, just because of what we just observed. Okay? In addition, the variance, I didn't even define what variance is, but we'll talk about this more. Okay? So there's something called the variance, and this will be calculated as np cubed. And that will be another calculation using calculus to prove. It's not that hard. But we will be using this a lot later. Okay? All right. So now I guess I'm running out of time, so let me now introduce the most generic form of the binomial distribution. Okay? So if x follows binomial distribution of np, then probability of x equals to k is given by n choose k, just as before. And then there's p to the kth power, and then q to the n minus kth power, where q is the chance of failure. If there's a p probability of seeing something, in our previous case it's the seeing a 6, right? Then the probability of not seeing a 6 is q, which is 1 minus p, right? Okay? So that's what you have. That's called the binomial probability. And then there's another one, which is if n is 1, okay, if n is 1, then you just have two cases, right? P of x equals to 0 or P of x equals to 1. Now, and because it's 1, so it's, if you have one item, 1 choose 1, you can check that this is 1, and then 1 choose 0 is also 1. Anything choose 0 is 1 because there's only one way to not choose anything. Okay? So n choose 0 is always 1. But if you have only one item, number of ways to choose one item from one item is 1 as well, right? Yeah. You can also just use the formula to get that as well. So this will be both 1 in both cases. But then, so this will be just 1, and what you get is, in general, let's just write it like this. In general, you just get pk 1 minus pk, 1 minus k. Right, q is 1 minus p, right? Now this case is called a Bernoulli trial. And I'm kind of going backwards because usually it's explained that the definition of a binomial distribution is a repetition of a Bernoulli trial. Okay? A Bernoulli trial is like you do something once, it has a success rate of p and failure rate of 1 minus p, and the probability distribution is this, okay? So this is the Bernoulli trial, which is a special case of the binomial PDF. And I have two other distributions I want to talk about, but I can't. Oh, let me just quickly do one last question, okay? So 30% of populations. Okay? And let's say this is some claim from a marketing department, okay? So you gave millions of dollars for your new brand of shoes or something, okay? So you have some new shoes, billions of dollars. And the marketing firm comes back and say, hey, you guys were basically nobody, but now after a lot of YouTube videos, 30% of the population now knows your brand, okay? Which is quite good, right? Okay. But you want to know if it's true. So what you do is, what is the probability that 2 or less people out of 10 random people know your brand? So what the CEO does is like, really? Let me check. He goes outside and goes to the street, stops 10 random people, asks them, and out of 10 people, 2 said they know your brand, okay? And you're like, okay, 2. It's kind of less than 30%. Right? It's not 3. So could that be something possible? And that's like the following. The probability that one person will say, yes, I know your brand, would be 0.3, right? What's the probability that he's going to say, no, I don't recognize what that brand is? 0.7, 1 minus 0.3, right? And then because you're saying 2 or less, so it's like, if it's 2, then it would be 2 and then 8 with 10 choose 2, right? But then it's 2 or less, so you're adding 10 choose 1 and then something plus 10 choose 0, right? Well, we actually know what this is called. This is called what? If you add up not just that probability, but every probability before that, what is that called? Cumulative. So we can use the calculator. Go to the calculator. Second distribution. And you're going to choose this time. Go up. Binomial CDF. You click binomial CDF. Trials, 10 trials. You know the probability is 0.3. And X value is 2. And what do you get? 0.38. Right? So you get 0.38. What's that? Okay, possible, right? But what if it was different? What if the company said, oh, we've increased your brand name recognition to 70%. But you still go out and find only 2 people recognize your brand. How's that? That's very suspicious, right? So that'll be like changing 0.3 to 0.7. And if you do the same calculation with 0.7, what's the probability? 0.0015. What does that mean?
That would almost never happen.
Yeah, that almost never happened. And your marketing company is lying to you. You should fire them. Yeah. And that's basically what we're doing here. Statistics is powerful because you can calculate the probability that something happens, and if it's very low, then with some confidence you can call that's a BS. Okay.